3.1 Symmetry. One type of symmetry that a graph can have is called point symmetry. So this is the official mathy definition of point symmetry. Two distinct points, P and P prime. So we read that symbol as prime. So P and P prime are symmetric with respect to point M if and only if M is the midpoint of the line from P to P prime. And point M is symmetric with respect to itself. What that means is that if you have some midpoint, the shape is symmetric if all the points on one side of the midpoint have a corresponding point on the other side of the midpoint. So here and here, obviously the line is symmetric. With this graph, you've got some point here that corresponds to a point here. You've got a point up here that corresponds to a point here. So any point on the shape, you can draw a line through the midpoint and then have another point the same distance away. Same thing with this function, right? It goes through the midpoint, and there it is. If I've got some point here, if I draw a line through the midpoint, and it corresponds to a point here. This point down here corresponds to a point up here, and so on. The origin is common point of symmetry. So here are the graphs of f of x equals x cubed and g of x equals 1 over x. So this point goes through the origin, and there's the symmetric point. This point, you draw a line through the origin, and there's the symmetric point. Same thing here. So again, the formal definition of symmetry with respect to the origin. The graph of a relation S is symmetric with respect to the origin if and only if some point AB is an element of S implies that negative A, negative B is also an element of S. Function has a graph that is symmetric with respect to the origin if and only if f of negative x equals negative f of x for all x in the domain of f. I don't necessarily need you to write this down. You don't need to write this down if you don't know what it means. I will put these formal definitions into the videos because it's important for you to get used to seeing them and get used to this kind of notation, but don't just copy this down. Write this down in your own words. So what does all of this mean? It means that if we have some function and we have some point a, b that is in the function, and the function is symmetric with respect to the origin, that means there has to also be a point negative a, negative b that is also in the function. The other rule that we can use is a function is symmetric with respect to the origin if f of negative x equals negative f of x. Meaning, if we make the x negative, do we also get a negative y value? So if I have, let's say I have a basic cubic function, y equals x cubed, which we saw back here is symmetric with respect to the origin. So one point that is on this function is the point 2, 8. If this function is symmetric with respect to the origin, then f of negative 2 should be negative 8. That is, the point -2, -8 should also be in the function. And it's true, if you plug in -2 and you cube it, you're going to get -8. In order for a function to be symmetric with respect to the origin, this needs to be true for all x values in the domain. Another way that we can do this, we can do it by picking points, or we can do it more generally. So if I pick points, right, the point 1, 1 is on the function f of x equals x to the 5th. If I put -1 into the function, I'm going to get -1 to the 5th, which is -1. So -1, -1 is also on the function. 232 is on the function. F of -2 is going to be -2 to the 5th, which is -32. So -2, -32 is also on the function. But rather than just doing this with multiple points, we can also do it with x in general. So f of x equals x to the 5th. F of -x equals -x to the 5th. Now the rule is that it's symmetric with respect to the origin if f of x equals -f, or f of -x equals -f of x. So does this equal -x to the 5th? Yes, it does, right? When we raise a negative number to an odd power, we're going to get another negative number. So yes, it does, which means that this is odd, or is symmetric with respect to the origin, which means that it's odd, but we'll talk about that in a second. So TLDR, the answer is yes. Here, f of x equals x over 1 minus x. So f of -x equals -x over 1 minus -x, which is going to be -x over 1 plus x. Does that equal -x over 1 minus x? No, it does not. Right? -x over 1 plus x does not equal -x over 1 minus x. And to show that, we could have some point on the line, like asymptotic 1, x equals 2. F of 2 is going to be 2 over 1 minus 2, which is -2. So we have some point, positive 2, -2. Now, is it the case that if we make this first 2 negative, so f of -2 is going to be -2 over 1 minus -2, which is -2 over 3. Does that equal negative f of x, which would be a positive 2? No. All right, so if this were an odd function, we know that -2 is in the domain, or is on the function. It should be also the case that -2, positive 2 is in the function. But f of -2 is not positive 2. It's -2/3, meaning this is not an odd function. So what we just found is called a counterexample. And finding a counterexample is often the easiest way to show that something is not true. So here we show that this function is not symmetric with respect to the origin by finding a point where f of negative x does not equal negative f of x. Or we can show it, we can prove it for all x up here. Another type of symmetry is line symmetry. You can have functions that are symmetric with respect to the y-axis, like a parabola here. You can have functions that are symmetric with respect to a horizontal line. Actually, if it's symmetric with respect to a horizontal line, it is not a function because it fails the vertical line test. It's a relation that is symmetric with respect to the this line, y equals 3. And I really should fix that because this equation's wrong. It should be x equals y minus 3 squared. And here we've got an ellipse, which is symmetric with respect to this line y equals 3 and this line x equals negative 2. Again, we have the formal definition: two distinct points, P and P' are symmetric with respect to a line L if and only if L is the perpendicular bisector of the line from P to P'. The point P is symmetric to itself with respect to line L if and only if P is on line L. So what that means, again, right, is if this is the line of symmetry, then any point on one side of the line, we can draw a line perpendicular to the line of symmetry and hit a point on the other side of the line. And so on. Right here, we can draw a line and hit another point. This is the kind of symmetry that you learned about in, like, kindergarten. What we mostly care about is symmetry with respect to the y-axis, because again, things that are symmetric with respect to the x-axis are not functions. We would talk about these more if we were going to do conic sections, but I don't think we'll have time to do that this year. So the test, if some x value gives you both a y and a negative y value, then you're looking at something that is symmetric with respect to the x-axis. So, right, x equals y squared minus 4. If you plug in 2 for x, and we solve for y, we're going to get that y squared equals 6, which means that y could be the square root of 6 or the negative square root of 6. So we get two different y values for every x, so it's going to be symmetric with respect to the x-axis. For the y-axis, it's symmetric if two x values give you the same, two x values on either side of the axis give you the same y value. So this is our test if f of negative x equals f of x. So in this case, 2, 8 is on the function, and also negative 2, 8 is on the function. We changed, the x from 2 to negative 2, so we made the x negative, but we got the same y value. So determine whether the graph of xy equals negative 2 is symmetric with respect to the x-axis, the y-axis, both or neither. So we want to test it with respect to, so it may help us to put this as y equals negative 2 over x. And so it's symmetric with respect to the x-axis if one x value gives us multiple y values. So, for instance, if I put in x equals 1, then f of x equals negative 2 over 1, which is just negative 2. It does not give us more than one y value, so it is not symmetric with respect to the x-axis. So we know that there is a point 1, negative 2 that is on this function. We can also see whether if we make that point negative, if we make the x negative, is negative 1, negative 2 on the function. So f of negative 1 is negative 2 over negative 1, which is positive 2, which does not equal negative 2. So it is not symmetric with respect to the y-axis. So not symmetric with respect to either of them. It is, I believe, symmetric with respect to the origin, but that's not what the question is asking. And we can do this last part, the y-axis symmetry, more generally if we say, is f of negative x equal to f of x? So my function is negative 2 over x. F of negative x would be negative 2 over negative x, which would be 2 over x, which is not equal to the original f of x. So no y-axis symmetry. Determine whether the graph of the absolute value of y equals 2 minus the absolute value of 2x is symmetric with respect to the x-axis, y-axis, both or neither. So here we have a function. Let's pick some values for x and y. If x is equal to 1, then we plug in 1, 2 minus 2 would be 0. So y would be 0. If x is equal to negative 1, we plug in 2 minus 2x, also is equal to 0. If we pick x to be equal to 0.5, then the absolute value of y is going to be, could be, so the absolute value of y has got to be 1, but it could be 1 or negative 1, right? So the absolute value of y equals 2 minus the absolute value of 2 times 0.5, which is 2 minus the absolute value of 1, which is 1. So we get that the absolute value of y equals 1, which means that y could be negative 1 or positive 1. And the same thing if we pick negative 0.5. We're going to get that the absolute value of, if we pick negative 0.5, we're going to get, again, this becomes then negative 1, but that's still 2 minus the absolute value of negative 1 is still 1. And so we still get 1 and negative 1. So we are getting two different y values for the same x value, which indicates that, yes, it is symmetric with respect to the x-axis. We're also getting that when we make an x value negative, we get the same y value, or y values. So that indicates that it's symmetric with respect to the y-axis as well. And I think when you graph it, it ends up being a diamond shape. Something like that. Functions whose graphs are symmetric with respect to the y-axis are even functions. Functions whose graph are symmetric with respect to the origin are odd functions. I think I used some of this terminology a little bit earlier in this video, even though we hadn't talked about it yet. My bad. But even and odd functions. Some functions are not even or odd. So we had these functions before. We said f of x equals x to the fifth is symmetric with respect to the origin, so it's an odd function. G of x equals 1 over 1 minus x was not symmetric with respect to the origin, and it's not symmetric with respect to the y-axis, so it is not even or odd. So, even functions have the y-axis symmetry, odd functions have the origin symmetry. Hint: odd functions look the same upside down as right side up. So a quick way that you can check the graph of an odd function is to turn it upside down. Watch this. Wow, it looks exactly the same. Look at that. Amazing. And that's it for symmetry. Tune in next time for parent functions. Ooh, sounds like fun.